Hello, chemistry team. Chemistry coach coming at you for video number 9, our last one for our chemical compounds journey. We are going to look. The last video we did how to determine empirical and molecular formulas given a percent composition by mass, which hopefully you had done before in high school or introductory chemistry. But this probably will be new for you. Combustion analysis. It's the same concept. Literally all the rules we're going to be using for empirical formula determination that we did last video will be exactly the same. So if you need to review that, great. I'm not going to set up all the instructions for it. We're just going to jump right into it. Combustion analysis is just another way to figure out the composition of some kind of compound. Now, these compounds have to be a specific type. They have to be combustible. We must be able to burn them, right? And the focus, typically, pretty much every problem I've ever done would be some organic compound, which is a hydrocarbon-based. It's got carbon, hydrogen, maybe some oxygen in there, other species. I'm going to limit it to carbon and hydrogen compounds, possibly as well with oxygen typically. Right? And what we're going to do, when you burn something, you are reacting it with oxygen gas, right? Boom, and you can get it straight out of the air. Not a big deal. So we'll take some organic compound, which contains carbon and hydrogen and possibly an extra element in there, usually oxygen. Burn it in oxygen, right? Combust it. And as long as you have excess O2, so I'm going to put excess here. We want to make sure every single atom of carbon and every single atom of hydrogen are reacting to form our products. So what happens is any carbon in that organic compound turns into carbon dioxide, as long as you have excess O2 gas. Right? All the hydrogen in there will turn into water. Now, the states don't matter at this point. We just want to know carbon converts to CO2 and hydrogen converts to H2O. If there's any oxygen in that species, right, because you're adding excess O2 anyway, you'll end up with a bunch of leftover oxygen floating around. So we are not able to determine the amount of oxygen directly from combustion analysis. Only carbon and only hydrogen. Now, if there happens to be oxygen, the third element, I can get that indirectly if I know the mass of my sample, right? Mass of the sample will be mass of all the elements. If I know all the elements except one, I can just subtract those from the mass of the sample. What's left over must be that particular element. Be it sulfur, nitrogen, oxygen, chlorine, doesn't matter what it is. So that'll be stated in the problem. So this is just one special way to do an empirical formula determination. Think of it as an extra step, like step 1A or something. Hey, let's take the combustion analysis. Let's figure out the mass of carbon and the mass of hydrogen, and then we're off to the races with our empirical formula table. All right, let's take a look at really quick how it works experimentally. It'd be fun to do in a lab, by the way. So maybe if you become a chemistry major, you'll be able to do that. And then we'll just do an example problem and be off to the races. All right, experimentally, this is actually kind of fun. It's always fun to burn things, right? Maybe you'll be able to use a bomb calorimeter or something when you get to a higher level. Woo! Wait till thermodynamics. So this is a real oversimplification of the technique. So let's say we've got some kind of furnace here where we can heat something up to a really high temperature, right? And we're bleeding in excess oxygen gas. So maybe you connect an oxygen tank to it or just bleed air into there. My concern with air is you've got nitrogen in there as well. So if you get it too hot, you might get some nitrogen compounds too. That might not be good. All right, so let's say we've got some kind of tray or something, and we've weighed our sample. Either we weigh the tray, put the sample on it, weigh the tray and the sample, subtract it. We got the mass of the sample, or we measure the mass of the sample some other way. But we got the mass of our organic sample there. Either it's a hydrocarbon or a hydrocarbon with carbon, hydrogen, and oxygen, something like that, right? Burn it! So all the hydrogen becomes water, all the carbon becomes carbon dioxide, and there'll be some leftover O2, right? And any oxygen in the sample ends up as in the O2 as well. So that bleeds through to another chamber. And in that chamber, we'll call that a water trap. So water that comes through, maybe there's some kind of chemical species on a pan or whatever. Maybe we can weigh it directly, or maybe we weigh this trap ahead of time. And it's got some chemical that's water absorbent, and all the water that comes through sticks to it or gets absorbed by it, increasing the mass. So we can just measure the mass difference and get the mass of water. Right? So that'll give us the mass of water that we got after combusting the hydrogen. Now we're going to find out we can take that mass of the water and back calculate to get the mass of the hydrogen in the original sample. Now this does not affect carbon dioxide or oxygen. Those just go straight through to the next chamber. So all the water's pulled out in the water trap. Now we got a carbon dioxide trap. Same idea. Maybe we have some kind of collecting trap or whatever we'd weighed ahead of time. It's got some chemical in there that's absorbent to CO2 only. The CO2 comes in, we measure the mass increase. That will give us the mass of carbon dioxide. And once we have the mass of the CO2, we can back calculate and get the mass of the carbon in the original sample. Pretty slick, huh? And then all the oxygen that's left over bleeds out. This is why you can't determine the mass of oxygen in the sample from the experiment itself, because it mixes in with the excess O2 that you're using to burn the sample. Ho-ho! So if there's oxygen in the sample or any other element, we'll have to figure it out through the back door by subtracting the masses of hydrogen and carbon from the mass of the original sample. So really, combustion analysis, mass of the original sample, mass of the water produced, mass of the CO2 produced. So let's put this here. So we'll get the sample mass. That's it. 3 pieces of data. So you'll recognize these problems on exams or quizzes by saying, hey, a particular hydrocarbon sample or organic sample containing carbon, hydrogen, oxygen, whatever, I'll specify what elements are in, undergoes combustion or it goes through combustion analysis. And I'll give you the mass of the sample, producing X amount of grams of water, X amount of grams of carbon dioxide. Hey, and from that we can get the masses again of carbon, hydrogen, and then the third element if there is one by default, and then we just go straight to our empirical formula table. Convert the masses to actual number of moles, et cetera, relative number of moles, multiply by integers if you have to, and you're good to go. So let me show you real quick how to go from the water mass to the hydrogen mass and the carbon dioxide mass to the carbon mass, just generically. Real quick, this is generically our first step in combustion analysis. Right, we got the mass of the sample, we got the mass of the carbon dioxide collected, and the mass of the water collected. So we want to get back and figure out, well, what's the mass of carbon in the sample, and what's the mass of hydrogen in the sample? So take the mass of carbon dioxide provided, convert it to moles, right? We got to get to moles because we can use the formula of CO2 to go from moles of CO2 to moles of carbon specifically. Remember, chemical formulas are conversion factors between the chemical formula and any element within it. So use the molar mass of carbon dioxide. So you've got 12.011 for the carbon plus 15.9994 for the oxygen times 2. Good to 3 decimal places from the carbon based on my periodic table that I use. So 1 mole of CO2 is 44.00980 grams. Good to 3 decimals. That converts to moles of CO2. Now notice if you have 1 mole of CO2, that has 1 mole of carbon and 2 moles of oxygen. We're interested in carbon. So 1 mole of CO2 came from 1 mole of carbon from the sample. It's a 1-to-1 ratio. And then 1 mole of carbon is 12.011 grams of carbon from our trusty dusty periodic table, which you probably have memorized by now. That'll give you the grams of carbon, limited by the significant digits, probably in the mass. I don't think the molar or atomic masses are going to limit you. We do the exact same thing for water. So take the mass of the water that was collected in the water trap provided for you. Use the molar mass of water to get to moles of water. So water, you got 1.00794 times 2 for the hydrogen, plus 15.9994 for the oxygen. Looks like we're good to 4 decimal places. I get 18.015280 grams per mole. Put that dashed line between the 2 and 8, good to 4 decimals. Now this is where most people screw up, if you want to put a little star right here. 1 mole of water contains 2 moles of hydrogen. Remember, CO2 is 1-to-1, but the hydrogen to water is 2-to-1. 1 mole of water, it's H2O, right, is 2 moles of hydrogen. And then multiply by the atomic mass of hydrogen, 1.00794. That will give you the grams of hydrogen limited by the significant digits there. So that's the first step, and then we'll just subtract those from the mass of the sample to get the mass of any third element if it's there, and then we're off to the races on the empirical formula. So keep that in mind, just pretty straightforward, nothing new here, just straightforward, line equations that we already know how to do from stoichiometry. Let's put a problem on the board and have at it. Real life stuff. This is a lot of information, gang. They're very easy to recognize. Combustion analysis problems are easy to recognize because you'll see combustion or CO2 mass, that kind of stuff. So let's say we have a 0.225 gram sample of caproic acid. Now, if you happen to know the formula for that, Merry Christmas. I'm assuming you don't, because that's an old common name. So you're not going to get the formula from that unless you memorize it. Pretty smelly stuff. It's carboxylic acid. Blah. That contains carbon, hydrogen, and oxygen. I would have to tell you. You can assume it contains carbon and oxygen, but it wouldn't be intuitively obvious it contains, carbon and hydrogen. Not intuitively obvious it contains oxygen unless you recognize that's a carboxylic acid, right? So I'll tell you there's carbon, hydrogen, and oxygen in it. They're combusted, and 0.512 grams of carbon dioxide are trapped, and 0.209 grams of water are trapped in the process. 3 pieces of information you get in combustion analysis. The original mass of the sample, the mass of carbon dioxide trapped, and the mass of the water trapped. Boom, we can do this. Notice A and B. Oh no, what is the empirical formula of caproic acid? We're just going to set up our table like we did last time. And then B, in a separate experiment, right, maybe from a mass spectrometer or something, the molar mass, they could do molecular mass as well. The molar mass of caproic acid is found to be 116.2 grams per mole. If it was molecular mass, it'd be 116.2 Daltons or atomic mass units or something. What is the molecular formula? So just like we did last time, we'll figure out what N is by taking this molar mass divided by the molar mass of the empirical formula to figure out what N is, that integer that relates the molecular to the empirical formula. I highly recommend you pause this. Give the combustion analysis part a shot. Take the mass of carbon dioxide, figure out the mass of carbon from it. Take the mass of water, figure out the mass of hydrogen from it, like I just showed you. Subtract those from the mass of the sample. That'll be the mass of your oxygen. Now you've got the 3 masses, carbon, hydrogen, oxygen. Set up your table, convert those to actual moles using molar masses. Divide by the lowest to get the relative number of moles. If they're all integers, you're done. You got the empirical formula. If they're not, if you've got third or half integers, multiply them by 2 or 3 or 4 to get it like we've done before. And once you got the empirical formula, figure out N and do the molecular formula. Come on. Test yourself. I'm going to erase the board and do the combustion analysis part. All right, let's see if we got the same thing. And this is just the prequel to the problem we did in the last video with the empirical formula. Oh, man. It's just the extra initial step. All right, here we go. Just like we showed, let's take the mass of carbon. Now, I don't care which one you do first, hydrogen or carbon, doesn't matter. So let's take the mass of carbon to solve for it. We got 0.512 grams of carbon dioxide. Divide by the molar mass of carbon dioxide, the 44.00980, good to 3 decimals, per mole. 1 mole of carbon dioxide contains 1 mole of carbon, and then multiply by the atomic mass of carbon, 12.011 grams per mole, and I get 0.13973 grams of carbon, good to 3 significant figures. That's how much carbon there was originally in our caproic acid sample. Right? Assuming we added excess oxygen and the caproic acid sample was the limiting reactant. And every single atom of carbon reacted, no side reactions, nothing like that. Real life may not be so simple. That's why we have experimental error, right? Let's take the same thing, the mass of water now to get the mass of hydrogen. So 0.209 grams of water. Divide by the molar mass of water, 18.015280. Good to 4 decimal places because of the oxygen limiting us. That gives us moles of water. 1 mole of water from 2 moles of hydrogen, don't forget the 2 there, and then multiply by the atomic mass of hydrogen, 1.00794 grams per mole, and limited to 3 significant figures as well, I get 0.023386 grams of hydrogen, good to 3 sig figs. So that's what we got from the combustion analysis. Now we know there's also a third element, oxygen, in this one. Can't get it from the combustion analysis, so we're going to get it by subtracting the masses of the carbon and hydrogen from the sample mass. So the mass of oxygen is the original sample mass, which I gave you, minus the mass of carbon, which we solved for here, minus the mass of hydrogen, which we solved for there. We're doing subtraction, so we're limited by the fewest decimal places or largest absolute uncertainty. So the original mass of the sample was 0.225 grams, probably measured on a milligram balance, minus the 0.13973 grams of carbon, good to 3 decimals, minus the 0.023386 grams of hydrogen, get to 4 decimals. Looks like we're limited to 3 decimal places. So I get 0.06188 grams of oxygen. So those 3 decimals gives us 2 sig figs in the long run. Now you can double check it. Take the mass of the oxygen plus the mass of the hydrogen plus the mass of the carbon. It had better equal 0.225 grams. That's the mass of your sample. If it doesn't, we screwed up somewhere, my friends. So now we have the masses of all the elements. So let's go straight to our empirical formula table. Take the mass of the elements, convert them to moles, actual number of moles, then relative number of moles. Do it if you haven't already. I'll erase this and get the next board up. These are long problems, but they're not terribly difficult if you know what you're doing. Here we go. Let's walk through this. List up exactly like we did before. We're just back to the last video. Let's take the masses of all the known elements, carbon, hydrogen, oxygen. Always use non-rounded values, right? Don't round it and then round and round and you get a rounding error. Let's take the mass. Now we got to convert to the actual number of moles. So look up the atomic mass on the periodic table. My guess is you've probably memorized these 3 already. Let's take the carbon, which is 12.011 grams per mole. Let's take the hydrogen, 1.00794 grams of hydrogen, right? Per mole. Got those memorized yet? I give it to you on a test. You don't have to memorize it, but you will. It's unavoidable if you use it enough. Oxygen, 15.9994. 999. That's my absolute favorite atomic mass. I like lead too. Lead is 207.2. It's got the 1 decimal point. It's kind of nice. 15.9994 grams of oxygen per mole. So we're limited to 3 significant figures for the carbon moles, 3 significant figures for the hydrogen moles, and 2 significant figures for the oxygen. Yes, we are. Yes, we are. Yes, we are. Let's see. I waste so much time to get into different colors, right? So carbon, I get to 3 sig figs, 0.0116. Here's my 3 sig figs. Pop the vertical dashed line. Give me 2 or more past that. I just do 2. 3 moles of carbon. So that's the actual number of moles. Let's get some blue here for the water. What did I get for water? 0. We're 3 sig figs, right? 0.023201 moles of hydrogen. Right? It's going to be very close. We're dividing essentially by 1 pretty much. So it's going to be very close to the original mass. Right? So it shouldn't be a big deal there. Where's my color for oxygen? So oxygen, take that divided by the atomic mass. I get 0.003867 moles of oxygen, right? Those definitely are not integers. They never are. So we need the relative number of moles. Let's make them all relative. So find the lowest of these 3. Let's see. Looks like that one. Looks like the oxygen. I'm going to divide them all by that number. Not with the moles, though. I'm just going to divide them all by that number. 0.003867. Let's do the same thing with the hydrogen. 0.003867. Same with the carbon. 0.003867. We're going to be stuck with 2 significant figures because we're dividing by the actual number of moles of oxygen in this case. So for carbon, we got 3 there, 2 there. If we look at the relative number of moles to 2, that really limits our sig figs, doesn't it? I get 3.0. There's my 2 sig figs, 3.008 moles of carbon. That's pretty close to 3, right? So, but we don't know. We might end up with a third or half integer on one of the other ones. So don't round that to 3 yet. Let's see. We might have to multiply that by some kind of integer. Let's do the hydrogen. Let's take the 0.023201 divided by 0.003867. Good to 2 significant figures. So for hydrogen, I get 5.9. Vertical dash line, good to 2 sig figs, 5.999. So that looks pretty darn close to 6 for me, so things are looking pretty good. And when I take a number divided by itself, I don't even need a calculator for that one. So that, just 2 sig figs, would be 1.000 moles of oxygen. Now look at that. I don't have any 1.5s or 3.33, so I don't have to do, I think it was step 4, where if you don't have integers for the relative number of moles, you multiply them all by 2 or 3 or 4. That happens every once in a while. Don't expect that on my exam, though. That means I can just round this. That's close enough to 3. So I'm going to go 3 moles of carbon. And for oxygen, that's close enough for 6. Let's go 6 moles of hydrogen. Duh. I look at the H and I write a C. I don't understand it sometimes. And then this is just 1. There we go, right? Hey, we skipped the whole step. Nice, isn't it? So we can write the empirical formula for this. What do we got? 3 carbons? How many hydrogens? 6. And 1 oxygen. Now, this is part A. That's not necessarily the true formula. Now, if N is 1, then the molecular and the empirical formulas will be the same thing. But that'd be pretty boring, wouldn't it? We need to do, for part B, to figure out the molecular formula, we need to know the integer ratio between the empirical and molecular formulas by dividing the molar mass of the true formula by the molar mass of the empirical formula. So I give you the molar mass of the true formula in part B, so we can figure this out. But let's calculate the empirical formula of this. So we've got carbon, 12.011 times 3, good to 3 decimal places. 1.00794 for hydrogen times 6. That's good to what, 5? 1.00794, counting on my fingers. That's 5 decimal places. Oxygen, 15.9994. There's only 1 of them. That's good to 4. So we're limited to the 3 decimals from the carbon. So let's do the molar mass of this. And if you add those all together on your calculator, you get to 3 decimal places. I get 58.08004 grams per mole. So we're going to need that to do part B. And all we need in part B is the true molecular formula. We'll divide it by that and see if we get a 1, 2, 3, or 4. All right? Let's do it. I'm going to obviously have to erase my board. It's all full of goodies. All right, I just summarized part B real quick, right? What is the molecular formula? If the molar mass, the true molar mass of coproic acid is 116.2 grams per mole. I think I stated it was determined in a separate experiment. And again, usually mass spectrometers. I got a video on quadrupole mass spectrometers I did when I was at UCI. I used to teach that. If you're interested in some crazy stuff and you're bored and there's nothing to do, I just took what we learned from the last board, the empirical formula, C3H6O, transferred it over to here. And then the molar mass of the empirical formula was the 58.08004. A lot of zeros in there. Good to 3 decimals. So I'm just going to take the true molar mass and divide the empirical formula molar mass. And cross your fingers, pray to the chem gods. Oh, please let this be an integer. If it ends up being a 2.34, we screwed up somewhere, and back to the starting board we go. That's never fun, is it? All right, let's take some brown here. So N is the true molar mass. And again, you could use molecular mass if it was given to you, not in grams per mole, in atomic mass units, Daltons, or something like that. And this will be the empirical formula, molar mass on the bottom. So what's the true molar mass? That's provided. You can't calculate that because you don't know what it is. So we have to measure that. 116.2 grams per mole. The empirical formula molar mass we calculated from our empirical formula. So 58.08004 grams per mole. Units cancel out, right? Boom, boom. Looks like 4 significant digits in the experimentally determined molar mass. Oh, getting old, arthritis. Yeah, it sucks. Getting old is not for weenies. What do I get for an integer? Oh, mama. 4 significant digits. I get 2. You can kind of see it looks like 2, right? 2.00068. I'd say that's close enough to 2. So we feel good. But if that was a 2.2 or a 2.3 or something, something's wrong. It's got to be really, really close to out to maybe the second decimal or something like that to be a true integer. If it's not, probably screwed up on the empirical formula molar mass or the empirical formula itself. That would be bad. All right, let's do this. So the molecular formula is the empirical formula times N. So what was our empirical formula? C3H6O times 2. So 3 times 2 is 6. So C6. 6 times 2 is 12. H12. 1 times 2 is 2. O2. There you go, my friends. This is how we do it. That is combustion. Sorry about that. I can't help myself. There's a song for everything in there. Now that doesn't tell us anything about connectivity of atoms, so we could probably get a whole bunch of different compounds with this same molecular formula with different connectivity called isomers, but that's for organic chemistry later. You got it, gang. We are done with this journey. Let's go to a new one. Love you guys. You're awesome.